Okay, we're going to use Lagrange multipliers to find the absolute extrema of f of x, y, z equals 2x plus 2y plus 14z on the sphere x squared plus y squared plus z squared equals 59. So in other words, this sphere, I guess it's centered at 0, 0. What's the radius? 0, 0, 0, actually. What's the radius? Square root of 59. So we're only allowed to plug in x, y, and z values into f that are on this sphere. Okay? So you can imagine that, right? You can imagine a sphere, only points on the sphere allowed in the domain or as the domain of f. And then this guy's just a hyperplane, isn't it? Does that mean a really a wiggly plane or something? I think of my son when I hear hyperplane because he's kind of hyper. No, it's just it doesn't exist. You can't graph it in 3 dimensions because it has an extra input, right? It has 4 variables altogether, 3 input variables. Okay. So what do we actually think of as our restraint? Even though here it doesn't really matter. X squared plus y squared plus z squared minus 59 equals 0. Good habit to get into, setting it equal to 0. So to make sure you have anything with a variable in it on one side. In this case, 59 is not a variable, so it doesn't matter. But we'll think then of this guy as our constraint function g of x, y, z. And when you set g of x, y, z equal to 0, yeah, it's a sphere. And that's our constraint surface then, not a constraint curve. Okay, so the method of Lagrange multipliers then says find del f, set it equal to some constant lambda times del g, which really means set corresponding coefficients equal, or corresponding components equal, right? I said coefficients because I'm used to teaching. You guys remember partial fraction decomposition? No. You just had it last semester probably. Bad memories. Didn't you watch my videos on Chamberlain's Calc 2 channel? Come on. Didn't you know about that channel when I wasn't your teacher? So that's if I say coefficients, that's why, because in that method you set corresponding coefficients equal. Okay, but here del f, lambda del g, set corresponding components equal, and then you have your system of equations. It's really easy to state the method, isn't it? But the devil is in those details, right? All right. It's kind of relaxing. Makes me want to go to sleep. Del f. What's del f? 2i, right? It's important to remember del f is a vector, so you could use the alligator brackets or that's component form or ijk. It doesn't matter. 2i plus 6j plus 14k. Not so bad, taking those derivatives, right? And then del g, let's see, partial with respect to x would be 2, leave a space, x, and then that's the I component, right? Plus, what's the partial with respect to y? 2y, that's the j component, plus partial with respect to z, 2z, that's the k component, and then remember we multiply through by lambda. You gotta be careful to not make your lambdas look like x's, because that can really throw you off, right? In the middle of a problem. So corresponding components, set them equal. What do we get? 2 equal, so this guy equals that guy. 2 equals 2 lambda x, right? This guy set equal to this guy. 6 equals 2 lambda y. This guy equals this guy. 14 equals 2 lambda z. There was one more equation. What is it? Yeah, the constraint, which I usually write in the original form. X squared plus y squared plus z squared is equal to 59. So you've got 4 equations and 4 unknowns. Easy, right? Well, not always, no. Well, the 4th equation is all in terms of x squared, y squared, and z squared, right? So if we can figure out what x, y, and z are, and again, this is the substitution method on steroids. If we can figure out what x, y, and z are in terms of the same variable, from the first three equations, we're in business. We can plug into the third equation and solve for that variable. In this case, I suppose it's not really, it's an unknown. Let's call it an unknown and not a variable. So in this case, what can we solve for in all three equations of the first three equations? You can solve for x, y, and z, and then it's in terms of lambda. Yeah. So that's my idea here. Now, to save time, okay, what is that? That's 1 equals lambda x in the first equation if you divide out the 2's. 3 equals lambda y if you divide out the 2's in the second equation. And what, 7 equals lambda z in the third equation. So is it okay to divide by lambda? Are we pretty sure that lambda is not equal to 0 here? Well, look at any one of the three, and what happens if you plug in lambda equals 0? You get a contradiction, don't you? Yeah, so like in the middle equation, or the second equation, if you plug in 0, you get 6 equals 0. If you plug in 0 for lambda. So dividing by lambda, since lambda is not equal to 0, a non-issue, right? And that you want to at least think about that when you do these. So, all right, so what do we get here? X equals 1 over lambda. Y equals 3 over lambda. Z equals 7 over lambda. And then the idea is to plug into the third equation, and you'll have everything in terms of lambda. So I'll do that right here. So we have plugging in for x, we have 1 over lambda squared. Plugging in for y, we get 3 divided by lambda. That's plugging in right there. 3 over lambda, and then we got to square it because y squared. Plus 7 divided by lambda. That's supposed to be a 7 squared equals 59. And remember, that's the same as 1 squared over lambda squared, which is 1 over lambda squared, plus what? 9 over lambda squared, right? Plus 49 over lambda squared. And then what do you get on the left side? Like you have common denominators, add them together, what do you get on top? That's a miracle, right? 59. Okay, so, but actually it was fun. I remember making these problems, and it was fun because you kind of work backwards, and you think, okay, what do I need to put here? I add these, I need to put 59 here, and then it works out. So in real life, you can expect ugly decimals, but in this class, you're not trying to learn arithmetic, right? So I try to make, even though they are not very easy equations compared to other ones you've seen in your past, they could be a lot uglier, right? Count your blessings, is that what I'm saying? I don't know. Anyway, what do you get? You can divide out the 59s. 1 divided by lambda squared equals 1, or lambda squared equals 1. Well, lambda squared equals 1, and then lambda, yeah, definitely equals plus or minus 1. Little bit of room there. And so lambda would be, if you take the square root of both sides, plus or minus 1. 2 cases then, right? What happens when lambda equals 1? What happens when lambda equals negative 1? Well, I mean, that's what these equations are for, right? We really, lambda is a means to an end. We want to get x, y, and z, don't we? So if lambda is equal to 1, what do we get? We get, what's the critical point? X is 1, right? Y is 3, and z is 7. And then what if it's negative 1? Negative 1, negative 3, negative 7. Only 2 critical points. Good deal. So I'm not even going to bother making a table. I'm just going to say, hey, I bet f of 137 is your absolute maximum. Let's see what it is. You'd have to plug in 1 here into the original function, right? 3 here and 7 here. So you get 2 plus 18 plus, what's 14 times 7? Plus 98. What does that turn out to be? 118? I guess I could have done that in my head, huh? Does everybody believe that? Well, is it going to, do I need to think a whole lot about what it is if all the coordinates are negative? Negative 118. Okay. So this guy is your absolute max. This guy is your absolute min on the constraint. That's a pretty problem. Come on. A little bit? Give it up a little bit. No.